Here's something else that you probably wouldn't hesitate to do given your experience with quadratic functions. The derivative with respect to x of the quantity x cubed minus 7x squared. Okay, when you have a quadratic, you simply do the derivative of the first term plus the derivative of the second, and the derivative of the third. Of course, the third one is 0, but that's okay. So that you have this instinct to do this. So we take the derivative of x cubed, which as you know is 3x squared, and subtract the derivative of 7x squared, which as you know is negative 14x. Well, that's wonderful, and it turns out that you can do that, but we haven't really proved that it works except for quadratic functions when we derived the expression for the derivative of a quadratic. Okay, so all this is implicit in what we did when we derived the derivative of the quadratic, but we haven't proved it for anything but quadratics. So what we've actually done here is we say that the derivative with respect to x of x cubed minus 7x squared is, well, derivative of x cubed minus the derivative of 7x squared, more or less distributing this derivative sign or expression through this function. And then we can bring the 7 out in front of here. Now we just proved that we can do that because that's just a constant times the function. We can bring the constant out. And having done that, we apply the power rule, which we're safe in doing. Derivative of x cubed is 3x squared. The derivative of x squared is 2x. And then we just simplify the expression and we're home free. However, we better prove that when you take the derivative of the sum of two functions, what you get is the sum of the derivatives. We want to show that the derivative of f of x plus g of x is indeed f prime of x plus g prime of x. Well, the limit as delta x goes to 0 of the difference quotient that we get for this function is just expressed here. You have your function f of x plus g of x, you evaluate that at x plus delta x, and then you subtract what you get when you evaluate it at x, and divide by your delta x. Now, we can easily rearrange this. We can take the f of x plus delta x minus f of x and divide that by the delta x, and then we can add the g of x plus delta x minus g of x divided by delta x. And this looks like the difference quotient for f of x, and this is the difference quotient for g of x. Now we do this magical thing and distribute the limit over the addition. Again, be a little uncomfortable. We haven't proven we can do that, but we're going to do it anyway. And then we say that, well, we got the limit as delta x goes to 0 of the f of x difference quotient, and the limit as delta x goes to 0 of the g of x difference quotient. And of course, this limit is f prime of x, and this limit is g prime of x. So as long as what we've done with the limits is valid, the rest of it is just simple algebra and the definition of the derivative. And we've proved that the derivative of the sum of two functions is the sum of the derivatives. Now, of course, over here we did a difference of two functions, not a sum, but a sum is just, we could write this as x cubed plus negative 7x squared, and then we'd be able to use this property here and proceed.